here we have a 1-bit adder with inputs A, B, and carry, which I will refer to as C. Carry being the previous computation's carryover, which basically tells us whether or not we need to account for a carry in this current computation. And the outputs of this adder are A plus B, and A plus B is not the logic notation for A or B, but rather A plus B, so the sum or the result of adding those two, and again accounting for the carry. And another output is the carryover, which again will signify the next operation, whether or not they need to carry. So as you can see, it's kind of a chain. Now I know it doesn't make sense to have a carry and carryover for a 1-bit adder, and honestly it doesn't. But we're just going to do it like this so we can sort of understand how it just functions as a whole. Because as you can see, or as you will see when we start to create 4 and 8-bit adders, that if you can understand it from a 1-bit adder perspective, it makes it much easier to just keep adding components. And literally, you can build an n-bit adder once you understand the fundamentals of what I'm about to show you. Okay, so let's just get started. Again, we have our truth table here. I'm really not going to do anything too crazy here by stating, all the values. So I'm just going to go over and we're just going to try to solve this. Again, this is going to be a 2-part video. We're going to do the first component, A plus B, and then we'll do the second component, the carryover. So let's just get started. First, we're just going to start underlining the conditions where A plus B is true. And then we're going to write some, what's the word I'm looking for? Starts with a P, predicates that fulfill these conditions. So let's look at the first one. The first one's not A and not B and C. The second one, sorry, it's a bit my table is not really that good. As you can see, I clearly lack the organizational skills necessary to make truth tables. Thought my other previous truth tables were okay, but I guess this one was just poor. So the next one is this time it's B's turn to be true, and everything else is going to be false, and not C. And the next one looks like A is true. Hopefully we can see a pattern here. Looks like only one out of the 3, only one can be true. And then we have the last one, which sort of sticks out like a sore thumb. All of them are true. So let's get started with trying to create a circuit. Now, technically, again, what we could do, we could be extremely lazy. We could just create the circuits necessary to fulfill all these conditions, and then OR them all together, and we would create a legal, a legal circuit to solve this. But again, we're trying to understand how these things, truly exist. So let's take things a step further, like we always do. I would like to think, and try to understand how these adders might truly manifest themselves. So I'm just going to scroll down. Hopefully, maybe I should rewrite those or something. Oops, scroll down a bit too far. So I'm just going to rewrite them real quick. I probably should have written them down here now that I think about it. And C, not A, and B, and not C, and A, and not B, and not C. Okay, so again, it seems to be that the common thing between these is that one of them is true, that one must be true, and the others must be false. Now, when I say that one must be true and the others must be false, what do we think of? If we look back to our previous logic gates, there is one specific logic gate that comes to mind that helps me describe this behavior that I'm talking about. Hopefully, maybe you guys can pause the video real quick and try to solve it. 3, 2, 1. Okay, hopefully you guys didn't cheat or anything. But it's the exclusive OR gate. Again, please recall that the exclusive OR gate, one of the conditions must be the exclusive OR gate returns true if and only if one of the conditions is true. So if A or B is, A must be true and B must be false, or B must be true and A must be false in order for the gate to yield true. right? Now, but we have 3 here, so what are we going to do? Well, we just simply have to take 2 of these components, exclusive OR them, and then exclusive OR that result with the 3rd component. So here, I'm just gonna write it down. A, B, and C. Recall C stands for my carry. I'm just gonna switch colors. So maybe what we might expect is something like this. Please again forgive me for my poor drawings. Looks like a pretty good exclusive OR gate. And now I'm going to take this. Oops, I do not want to do that. And I'm just going to take this, and I'm going to exclusive OR them together. And then hopefully our result should be A plus, sometimes my tablet's not responsive, A plus B. Now again, there's still the last condition, which we haven't necessarily done yet. Oops. But we'll get to it. We're just solving for this first. Let's just see what happens here. So let's just go over it, right? Let's just answer let's just go through the table, I suppose, and see what we get. I'm going to use green as for my colors. So let's test it. So we have 0, 0, and 1. Okay, 0 and 0. Well, that'll pass 0. Then we have our 1. Well, one of these, C is true, and the exclusive OR for AB is false. So the output is going to be true. And indeed, this fulfills our first condition. So check. Let's get our eraser out. Hopefully I can make this video pretty quick. Probably have to be a bit faster with this. Okay, so our next one, B is true, and C is so B is true and the others are false. So okay, look here. Okay, AB. Okay, this is 1 and this is a 0 again, and as we can see here, 0. So that passes the test. The second primitive passes our circuit. And look at the last one, A is true, so, I mean, you guys should hopefully see it at this point. Yes. Sorry if you guys follow along. I'm trying to make this video a bit short. I mean, I'm just really doing redundant stuff right now. So, yeah. So, currently our circuit that we've created fulfills these 3 predicates. Let's go up, and let's look at the last one. Let's just test it. A, B, and C. So, let's do A, B, and C. Okay, so A, B, well, you look at that. Because they're both true, they end up canceling each other. And, or not really they cancel each other, that's just but, that's sort of a way to think about it. Again, this is just the nature of the exclusive OR, this is how it functions. If both are true, it yields false. And look, C here is true, and we get true. So surprisingly enough, our circuit, well, not really surprisingly enough, but our circuit somehow managed to, make it weird, make it sound like magic and it wasn't intended. Please, I had it all calculated. Oh god. But yeah. So it ends up solving this last predicate too. In fact, this is actually the solution for the adder. You exclusive OR AB, and then take that result and exclusive OR with C, and you have the result of A plus B. Please feel free to go ahead and build this. Normally I like to show you guys the circuit diagram for this, but I'm not going to because I have the entire circuit built and I just want to show you the final product. Plus, it's going to keep eating up into the time that we barely don't already have. Hopefully my carryover thing is correct. Hopefully there aren't any mistakes. If there are, I'll fix it. But yeah, so here the truth table, and here's our circuit. Why don't you guys take time real quick and think about how you guys might implement the carryover yourselves. Hopefully you guys are able to think about how you would do this one. And again, so next video we'll be looking at how to make the carryover for our 1-bit adder. And then later on we're going to just combine them to create a full adder. Okay guys.